Chapter 19, The Nucleus, A Chemist's View. Our outline is nuclear chemistry, applications, differences between chemical and nuclear reactions, the nucleus, nuclear decay processes, rates and disintegrations, and nuclear energy. So, in general, here's some definitions. Nuclear chemistry. It is the study of the nucleus and its reactions. A nucleus is radioactive if it changes spontaneously. The process by which an unstable nucleus changes is called radioactive decay, or nuclear decay, or perhaps some other name. All isotopes of all elements beyond bismuth are radioactive. That means polonium and beyond. Radioactivity is produced by nuclear decay. So our next topic is applications. There's a lot of applications. Here are some of them. Radioactivity, the process thereof, is used to kill microorganisms. That could be to sterilize medical devices. That could be to preserve meats and fruits and vegetables. So if they are exposed to the nuclear decay products, we will see alpha particles, beta particles, gamma particles, then that kills the microorganisms, for example, on the medical devices, on the meat, the fruit, the vegetables, and then those particles go away, leaving the medical devices, the food safe to consume, and having a much longer shelf life. It can be used for dating, for example, carbon dating. That can be done with materials that once lived, like on cotton material, flax. It works with carbon-14. It can be used in rock dating. So to date a rock to get a sense of how old that rock is or when it last underwent a geologic change. Radioactivity is used in medical areas. Radiotherapy is used to fight cancer. So often cobalt-60 is used, and it produces products that can be directed at a tumor, very, very directed, very localized into a cancerous tumor, leaving the rest of the body intact, hopefully, and just fighting that, just killing off that cancerous tumor. Tracers, radioactive tracers, can be used to study digestion, circulation of blood. Plutonium-238 is used to power heart pacemakers. Just for comparison, plutonium-239 is the one used in nuclear reactors and in nuclear bombs. Strontium-87 is used to study bone growth. Notice that way of writing the isotope, strontium-87. The 87 is the mass number. That would be written in another notation, a subscript to the left of the SR chemical symbol. And the mass number is equal to the number of protons plus the number of neutrons. They could be used as radioactive tracers, kind of like what we mentioned above, to study digestion and so on. They could be used to study chemical reactions. They could be used to study pipe leaks, to study uptake of fertilizer, for example. I have here listed an application to study a chemical reaction. So in that reaction, we have carboxylic acid, actually that's acetic acid. All carboxylic acids have C double bond O OH in them. When it's reacted with an alcohol, it produces an ester and water. Let's say that we were wondering if the OH on the carboxylic acid is completely replaced by the OCH3 on the alcohol in producing the ester, or if only the H on the carboxylic acid is replaced with only the CH3 from the alcohol. So what was done, at least in this reaction study, is to have the oxygens within the carboxylic acid be O16, the common isotope of oxygen, and the oxygen in the alcohol to be O18, that isotope, the less common isotope of oxygen. And then do the reaction and look at where the O18 is. If it's in the ester, then that means the whole OH of the original carboxylic acid is replaced by the OCH3 of the alcohol. If, on the other hand, the O18 shows up in the water, then that means only the H of the carboxylic acid was replaced. Well, it turns out it's on the ester, oxygen, so now from that then a chemist would know the whole OH is replaced by the OCH3 of the alcohol. Of course, we know that nuclear energy exists that uses these nuclear processes, nuclear chemistry. Bombs exist, nuclear bombs. Some differences between chemical and nuclear reactions. A biggie is energy, the energy difference. Nuclear reactions produce much more energy. Take, for example, burning of methane to give CO2 and water, and of course heat because it's an exothermic reaction. The heat per gram of methane is about 50 kilojoules. If we take uranium-235 and undergo a fission reaction with it, and that's an example of a fission reaction, U-235 plus N being a neutron, to give barium plus krypton plus 2 neutrons plus lots of energy, we find that the heat involved is about 70 million kilojoules per gram of uranium. Much, much, much more energy. That's fission. If we take two hydrogens and fuse them together to give helium, it gives off also lots of heat. Per gram of helium, it's about 100 million kilojoules. That is an example of a fusion reaction. So fission is breaking the nucleus into two isotopes. Fusion is putting together two isotopes to produce products. Both give off lots of energy. Isotopes make a big difference in nuclear reactions, but they don't in chemical reactions. That is, if we do the combustion reaction of methane, whether it contains C12 or C14, we still get CO2 and water. On the other hand, if we take C12, which is not radioactive, it will not undergo a nuclear reaction. But if we take C14, it will undergo a nuclear reaction. In fact, C14 is the one used in carbon dating. Rates of nuclear reactions are independent of temperature, pressure, catalysts, electric and magnetic fields, etc. When a nuclear reaction is going to happen, it happens. Whereas chemical reactions are very dependent on temperature, pressure, and catalysts, and so on. Nuclear reactions are independent of the chemical form, whether if we're going to do a fission reaction with uranium-235, whether we had UO2 or uranium, just the solid, a chunk of uranium metal, or UF6, they all would undergo the nuclear decay process. Nuclear reactions often make new elements. For example, when carbon-14 undergoes its process, its nuclear reaction process, it makes an isotope of nitrogen, that N14. Also, it produces a beta particle, which we'll get into. Radium-226 produces radon-222 plus an alpha particle. Okay, a little bit on the nucleus. It's composed of protons and neutrons, which you know of course. Those together can be called nucleons. So we could say the nucleus contains nucleons. The nucleus is very, very dense. Its density is about 10 to the 14th grams per ml. Compare that with the density of water, about 1 gram per ml. If the nucleus were the size of a ping pong ball, it would weigh 1 billion tons, and the electron would be about half a kilometer away. Kind of like put this ping pong ball in the middle of a baseball stadium, and the size of the stadium would be about the size of the atom. So the nucleus is very, very dense. And what is holding it together? What's holding these nucleons together? So just a little intro to the very basic forces from physics. They are the gravitational force, the electromagnetic force, the strong force, and the weak force. Gravity, of course, you are familiar with that one. That's what's holding us to the Earth. That's what's holding our moon around our Earth. That's what's holding the Earth around the sun, and so on. In comparison to the electromagnetic or the strong force, the gravitational force is the weakest, but it is the longest ranging force. The electromagnetic force, that would describe the force of attraction of opposite charges, or you could say north and south poles of magnets. In comparison with gravity and the strong force, it has a medium strength, it has a medium range. The strong force, so that's the one that is holding the nucleons together in the nucleus. It's, of those three, it's the strongest, but it's also the shortest ranged. It has a range of only about 2 nucleons. So it doesn't even go throughout the whole nucleus. And then there is this fourth one, which describes certain forms of radioactive decay. So the strong force is what's holding the protons and neutrons together, and it is responsible for the existence of the nucleus. Realize that the protons within the nucleus are repelling each other with the electromagnetic force, but they're also bound together with the strong force. So if 2 protons are very close together in the nucleus, the strong force holds them together. The strong force holds protons together, neutrons together, and protons and neutrons together. And it's much stronger than the repulsion between those 2 protons, provided they're close together. But if we have protons that are quite a bit spread apart in the nucleus, then the strong force is not holding them together anymore, and they are feeling some repulsion due to the electromagnetic force. Alrighty, so the nuclear decay processes, our next section. In the late 1800s to early 1900s, 3 common radioactive particles were discovered. They were named the alpha particle, the beta particle, and the gamma particle. Studying them, it was found that the alpha particle is attracted to the negative pole of an electric field. Therefore, it has a positive charge. The beta particle was attracted to the positive pole. Therefore, it has a negative charge. And the gamma particle was not affected by either, so it is neutral. We'll talk about each one of these. So, first, the alpha particle. When it's involved in a radioactive process, we could call that process alpha decay, alpha emission, alpha particle production, and there might be other names too. It turns out the alpha particle is the helium-4 nucleus. So we could express that as I've shown here, He2+, subscript 2, that would be the number of protons in helium, and that's called the atomic number. And then we have a superscript 4, that's the mass number, that's the number of protons plus neutrons. So that means the alpha particle is the nucleus of helium containing 2 neutrons. And the 2+ charge, because it's only the nucleus, so it doesn't have those 2 electrons. It can be symbolized with the notation alpha, with the 2, with the 4. We can also just symbolize it alpha. Radon-222 undergoes this alpha decay, and you see the reaction shown there. Notice that the way we balance a nuclear reaction is the superscripts on the left side have to equal the sum of the superscripts on the right side. The subscript 86 has to equal the sum of the subscripts on the right side. So 222 equals 218 plus 4, and 86 equals 84 plus 2. So if we knew that we had radon-222, we would write it out like that. If we knew it produced alpha particles, we would write the alpha particle, and we would figure out what other isotope it becomes by balancing. So what's happening is the parent nucleus is losing 2 neutrons and 2 protons, so it's becoming a little bit smaller. The mass number decreases by 4, and the atomic number decreases by 2. This process tends to occur in heavy isotopes. Isotopes we can also refer to as nuclides, where nuclides is referring to kind of like a single isotope. Isotopes can be a single one or can be a whole collection of them. So this process tends to occur in heavy nuclides, heavy isotopes. So there's how we balance reactions, nuclear reactions. Sum of the mass numbers of products has to equal sum of the mass number of reactants. The sum of the atomic number of the products equals the sum of the atomic number of the reactants. Alrighty, so there's one for you to practice with. We have that GD150 isotope. We know it goes by alpha decay. So what daughter nucleus must it make? And it turns out to be the one shown there. So at some point, just go back and make sure that you can do that. Thick paper and skin can stop the alpha particle, as I try to show in that picture there. The cells at the surface, if bombarded with alpha particles, tend to be killed rather than mutated by the alpha particle. Okay, next, beta particle and its process, which we could call beta decay or beta emission or beta particle production or some other name. It turns out the beta particle is an electron. We can symbolize it as I've done there, E subscript -1, superscript 0. The 0, because there's no protons or neutrons, it's only an electron. The -1 having to do with the fact that it has a -1 charge. We can also symbolize it just using the beta symbol with that -1, 0. As I've written, the -1 is not really an atomic number, but it turns out writing it helps in balancing. Alrighty, so carbon-14 produces beta particles, undergoes beta decay. Carbon-14 has 6 protons, as all carbon atoms have, carbon's nuclei have. Therefore, 14 minus 6, it must have 8 neutrons. And it produces N14, being N, it has 7 protons, and we would calculate then that it has 7 neutrons. So what we see is a neutron has been converted to a proton as the electron is formed. And by the way, the electron, that beta particle that's produced in the C14 beta decay, is not an electron from the electron cloud of carbon. Rather, it is an electron that is produced by that decay process. It is produced when a neutron becomes a proton, and then a byproduct is the electron. So in beta decay, always this is occurring. The electron is formed as a neutron becomes a proton. And we can see that in balancing. If we write the neutron, N, 0, 1, 0, no protons, 1, well, it's got a neutron. It is, in fact, a neutron. And then we write that yields the electron. And a proton would have the 1, 1 there because it is, well, a proton with no neutron. It tends to, oh, and you see that 1 on the left equals 1 plus 0 on the right. The lower 0 on the left equals 1 minus 1. It tends to occur when the nucleus contains too many neutrons. And we can determine that by comparing the mass number of the isotope that we're given with the molar mass for that element that we would get from the periodic table. If the mass number is large, then that means there's a lot of neutrons, and a common decay process that when there's too many neutrons, that isotope undergoes is beta decay. So beta particles can be stopped by thick paper. Actually, no, I take that back. That's alpha particles. They can be stopped by, for example, a 3 millimeter thick aluminum sheet. They are able to penetrate thick paper. They are stopped to some extent. The slower ones could be stopped, but the bulk of them would get through, and they would get through skin. But they could be stopped by metal. As the paper thickness increases, the number of beta particles absorbed increases, and beta particles can go 1 centimeter into flesh, and they damage cells as opposed to killing them. So that makes them dangerous in the sense of giving rise to mutated cells, which then can become cancerous. Okay, our last type of process that is one of those 3 is gamma particle production, which could be called gamma decay, gamma emission, gamma particle production, maybe gamma ray particle production. Turns out it is a photon, a very, very high energy photon, being that it has no protons, no neutrons. It has 0, 0 for both of those two. So if we look at the electromagnetic spectrum, the one that you probably have seen before in a chemistry or physics class, at the high energy end, it runs from gamma ray particles, these type we're talking about here, all the way to the low energy radio waves. So at the high energy end, at the very short wavelength end, we have gamma particles. Next, we have X-rays, then UV, then the visible light spectrum, then IR, then microwave, then radio waves. So wavelength increases as we go down in energy, and these gamma particles, they are produced by most nuclear decay processes. Being photons, they are massless, they are chargeless, they are very damaging. When uranium-238 undergoes this alpha particle production reaction, it also produces gamma radiation. Most nuclear decay processes produce some gamma radiation. And reason being that the daughter nucleus that's formed is often formed in a high energy state. That is to say, the nucleus is not in a ground state. Remember back to electrons, and when they jump up to a higher energy state in an atom, we symbolize that with an asterisk. You might have done it that way back in Chem 1. And they're in a high, those electrons are in a high energy state. They will very quickly fall back down to a lower energy state, giving off a photon of radiation. And that photon would be in the UV range or the visible range or the infrared range. Okay, so that's an electronic transition. When gamma particles are produced, it's the nucleus and the nucleons in there that are not in the ground state. They are in some kind of excited state, and when they fall back down to the ground state, they give off also electromagnetic radiation, but it's in the gamma range. They are very hard to stop. They can penetrate skin, thick paper, metal sheets. They can go right through the body. Okay, so these three nuclear decay processes are the most common, but others exist. And we'll look at those now. So other nuclear decay processes. Probably of those, the most common is positron emission. It happens, we could call that positron decay, positron production. And the positron, what's being produced, is a positive electron. It is the antiparticle of the electron. We can symbolize that as beta 10 or E, like electron 10. Notice that we have a 1 there as the subscript, not a negative 1. And that's a way to symbolize we're talking a positron as opposed to an electron. If a positron and an electron get together, they annihilate each other. They produce a lot of energy and they produce gamma rays. N13 is an isotope that undergoes positron decay. And we see the reaction there, N13 forming C13 plus the positron. Notice that the 13 on the left equals 13 plus 0 on the right. 7 equals 6 plus 1. And in what's happening here is a proton in the nucleus is becoming a neutron and a positron. So that's the underlying change that's occurring in the nucleus when a positron is produced. So we see that there, P11 yielding N01 plus beta 10. This process tends to occur when the nucleus has too many protons. So it's a way to cut down the number of protons. And what we would do is we would be given an isotope like N13. We would compare this 13 to the molar mass for nitrogen we see on the periodic table, which is around 14, and we would find it's less than the mass number is less than the molar mass, and so we would predict that the N13 would probably decay by positron decay. A less common process is electron capture. So that occurs when an electron in the electron cloud actually makes its way to the nucleus, and in the process it creates a neutron. It's rather rare because it takes two parts to be involved: the electron to fall into the nucleus and then to be absorbed by a proton. And isotope that undergoes that process is titanium-44. We see the reaction there. If you balance it, you'll see that the scandium-44 has to be the product. And in this process, a proton in the titanium is being bombarded by the electron from its own electron cloud to produce a neutron. So notice that that's how we would balance that reaction, so we know what the underlying process is that's occurring. And it tends to occur when there's too many protons in the nucleus, that is to say the mass number is less than the molar mass. Now, that is also how we go about predicting positron decay. Positron decay is much more common than electron capture. So if the mass number of the isotope is less than the molar mass of that on the periodic table, predict positron emission. Proton emission, so a proton can, a nucleus can simply kick out a proton, not very common. We see it occurs for scandium-43. Neutron emission, so the nucleus just kicks out a neutron, not very common either. That occurs with bromine-90. And then spontaneous fission, that's when a nucleus is unstable, it's big, it breaks to smaller nuclei, it's very rare to just be spontaneous. That occurs with AM-244. Okay, so here's a table from your book giving some information about these processes. So we have the process beta particle production, positron production, electron capture, not very common, alpha particle production, gamma particle production. Okay, so those are the ones we've talked about. Of those, the most common ones are beta particle production, positron production, gamma production, and alpha particle production. Alrighty, so here are some problems for you to practice just simply balancing. If we're told that carbon-40 reacts by electron capture, what would be the product? So I would say look at these later after you've gone through these notes and just make sure that you can balance them correctly. Just go by that first sentence that you were given. K40 reacts by electron capture. The next one, N20, sodium-22 decays by positron emission. And then U-238 decays by alpha emission. Our next problem is calculate X and Y for the decay of U-238 to lead-206. So it turns out that uranium-238, it's unstable, it decays, and it decays by many steps, actually 14, a total of 14 steps. We see all those steps here. So here's showing uranium decay series. So there's U-238 up at the top right corner, and it decays by alpha, then a couple betas, then many alphas, and then some more betas and alphas, till it finally is stable at lead-206. So if we were asked how many alpha steps, how many beta steps does it undergo, that's our problem there. Then we would write out the reaction as I've done there. We have as unknowns X, that is the number of alpha particles produced, and we have a known y, how many beta particles were produced. So by balancing, we can determine the value of x and the value of y. So the way I did it was to realize that 238 equals 206 plus 4x plus 0y, or 4x plus 206 equals 238. Calculate x is 8. And we have that 92 is equal to 82 plus 2x minus y. We know what x is 8, so we end up with negative y plus 8 times 2 plus 82 equals 92, or y equals 6. So later on, go through that and just make sure that you can do it. So note that this graph shows all the decay processes that uranium undergoes to finally be a stable isotope, this lead-206. By the way, this is not fission. This is the various decay processes that uranium-238 just naturally undergoes. So we see the processes and how many there are and so forth, but we do not know how quick they occur. One of those turns out to be the slow step, and that basically determines the half-life of U-238. Okay, our next topic has to do with stability, which is in the realm of thermodynamics. So this graph is a graph showing on the y-axis the number of neutrons, so number of neutrons on y-axis versus number of protons on the x-axis. And the red dots kind of going from left to right, up, going toward the right, those are showing for those various neutrons and protons numbers of, it's showing whether there's a stable isotope or not. So a red dot describes a stable isotope. The blue dots are the unstable isotopes that have those number of neutrons and protons. So this is showing all the isotopes, stable and unstable. And if we draw that red line showing the 1-to-1 neutron to proton ratio, we see that when the number of neutrons equal the number of protons, we have some stable isotopes, but that's only when we have a small number of neutrons and protons. As we get more and more neutrons and protons, we find that there are many more neutrons than protons required for stability, having to do with basically the repulsion between protons in the nucleus. So there are 279 stable isotopes. To be a stable isotope is to not undergo spontaneous reactivity, to not just have to change what the nucleus is. When the Z, the mass number, no, that's the atomic number, when Z is less than or equal to 20, most stable isotopes are stable. When the atomic number is greater than 83, so that would be from polonium and beyond, all the isotopes are unstable. And when there's too many protons or too many neutrons in the nucleus, then the nucleus is unstable and it undergoes some kind of a spontaneous nuclear decay. Too many protons, as we talked about before, usually results in positron production. Too many neutrons usually results in beta decay. And this is showing that if we have even number of protons and even number of neutrons, we tend to have lots of stable nuclides, stable isotopes. If one is even but the other is odd, there's fewer stable isotopes. If both are odd, there's very few stable isotopes. These have to do with kind of like magic numbers, sort of like we had magic numbers when we look at electrons. We have those 2, if there's 2 for hydrogen, that makes for more stability. If the atom, that's why 2 hydrogen atoms come together to form H2, because then each atom has access, or each nucleus has access to 2 electrons, kind of like 2 is a magic number. That works for group 1. Group 2, the magic number is 8, having to do with the octet, and that's why certain molecules combine. Well, there's magic numbers with the nucleons in the nucleus, and nuclei with numbers of protons or numbers of neutrons equal to 2, 8, 20, 50, 82, 126, they're usually stable. So looking at the helium nucleus, it has 2 neutrons, 2 protons, very stable. Tin 50 has 10 stable isotopes, as opposed to antimony 51. By that, I'm saying it wrong. Tin has an atomic number of 50, not a mass number. Antimony, an atomic number of 51. If we look up the number of isotopes of tin, we would find there's 10, versus antimony, there's only 2. So this kind of magic number idea. This is a diagram of a Geiger counter. A Geiger counter it has beeps for the having to do with detection of radioactive decay particles, and it works because it has a cavity that contains argon, and it has a space, a window, where if the Geiger counter is put up to material thought to be radioactive, if it is, then that radioactive material is producing alpha particles, beta particles, positrons, gamma radiation, depending on what the nucleus, what the isotope of that radioactive material is. And those particles enter into the argon atom chamber, and they cause the argon to be ionized, to be made into cations and electrons. And those, being mobile charges, can conduct current, and that the argon sample now is conducting current can be measured, can be detected, and so the Geiger counter is set to beep, to make a sound when a current is detected. So the more current, the more radioactive decay going on, the more beeps we hear by the Geiger counter. And here's some information just for you to read through on your own. Some of you may have heard of the Radium Girls, the whole incident where a dye was painted onto the face of watches a long time ago, because that underwent that material in it contained radium, and that undergoes radioactive decay, as we see from that reaction I'm showing there, to produce alpha particles, and it made the dye glow so that the watch could be read in the dark. Well, the women who painted this dye on to the watches' faces, they wanted to have a very, very fine paintbrush point, and they would dip it, they would put it in their mouth to make the point of the paintbrush very thin, and then they would dip it into the dye, and then they would paint with it. Well, doing that a lot caused them to have the radium in their body, and alpha particles are very dangerous when they're within our body, because then they're hitting our tissue and destroying our tissue. and our bones and so forth. So it killed a lot of people, but it was eventually detected and that process was stopped. But unfortunately, a lot of people died in the meantime. People had a thing for radiation. They thought that it was like a source of energy, where if they drank a drink containing radioactive, an unstable isotope like this radium, then they would have more energy. In fact, there were even these radiation health spas that people would go to feel more energetic. And a drink that contained the unstable isotope radium was manufactured, and people drank it, and one day they finally learned how dangerous it was. But anyway, take a look, read about that if it interests you. So now we'll get into rates of nuclear decay. So we have a parent, as it's often called, an unstable isotope that undergoes a radioactive decay process, producing a daughter and radiation, the alpha, the beta, the positrons. We talked about radium-226 producing radon-222 plus an alpha particle. 1 gram of radium-226 generates 3.7 times 10 to the 10th alpha particles per second. Or we could say that its rate of decay is 3.7 times 10 to the 10th disintegrations per second. So that's its rate of reactivity. It's also simply called, when we're in the nuclear chem world, just simply activity. So rate, as we first learned about it back in chapter 12, in nuclear chem, that's often referred to as activity. And that would be the number of reactions per second, the number of disintegrations, the original isotope disintegrating per second. We could call that DPS, disintegrations per second. The metric unit is BQ, it's called the becquerel, named after a scientist who studied nuclear decay. 1 becquerel is 1 DPS. Another unit is the Curie. 1 Curie is 3.7 times 10 to the 10th disintegrations per second, named after Madame Curie and her husband, who were very active in working with nuclear decay. Alpha, beta, and positron decay are all first-order decay processes. So when an alpha particle is produced, or a beta particle, or a positron, it's simply the nucleus just breaking down. So it's first order. It just takes the nucleus to break down. It's not two nuclei hitting each other. It's just the nucleus on its own good time breaking down. That's why it's first order. So here's just a reminder of a chemical kind of first order reaction. Let's say we have chemical A forming B, and it's first order. It just simply is A breaking down to become B. So when we worked with that kind of a reaction back in chapter 12, we looked at concentration of A versus time, for example. And being first order, the rate is equal to K, the rate constant, times the concentration of A to the first power. Or we could say concentration versus time, the concentration is equal to A naught, the original concentration of A, times e to the minus kt. If we wanted to plot the linear form of it, we would have ln of A equals minus kt plus ln of A naught. The half-life for that first order reaction is ln of 2 over k. Remember, k is the rate constant. Well, we have a completely analogous setup with nuclear decay. We have the parent forming the daughter. We work with often numbers of nuclei n. We will see that we can work with rate also. We will see that we can work with mass. But let's just say, okay, we're looking at how many nuclei are there versus time. So we would have that rate is equal to Kn, first order, so n to the first power. N versus time is given by that exponential decrease. N is equal to n naught, whatever the original number of nuclei were, times e to the minus kt, where k is the rate constant. The linear form would be ln of n equals minus kt plus ln of n naught. The half-life is given by t sub 1/2 equals ln of 2 over k, the rate constant. We can also think in terms of rate as a function of time. Rate is equal to rate naught, whatever original rate of decay, e to the minus kt. Ln of rate equals negative kt plus ln of rate naught. We can also think in terms of mass. So mass as a function of time is equal to m equals m naught, whatever was the original mass of the isotopes present, e to the minus kt, the linear form of it being ln of m equals minus kt plus ln of m naught. Okay, so n naught is just the number, the original number of nuclei present. N is the number of nuclei remaining at time t. How we get the rate equation from the n equation. So we start with n equals n naught e to the minus kt. So that equation is telling us how much n, how many nuclei are present as a function of time. Remember, n is the number of nuclei at time t, and naught is the original number of nuclei. If we take that equation and we multiply both sides by k, of course mathematically we're allowed to do that, then we have Kn equals Kn naught e to the minus kt. Kn is equal to the rate. Kn naught is equal to the original rate. So we have rate as a function of time is equal to the original rate e to the minus kt. Now, when we would use that equation would be when we're told we have an isotope that had an original rate of decay and has now this current rate of decay, because we can measure rate of decay, for example, with a Geiger counter. How many beeps do we hear per second? That would be rate. So maybe we have the original rate of decay, we have the current rate of decay, and so we could, for example, find the rate constant, ultimately the half-life. We would use that equation there, rate equals rate naught e to the minus kt. If on the other hand we're given mass, the original mass, the final mass, for example, then we would use the mass equation. So again, we're deriving it from the n, the number of nuclei equation. So we have n equals n naught e to the minus kt. Now, if we take that equation and we do the same things to both sides, we're okay mathematically. So what we're going to do is divide both sides by Avogadro's number. That gets us moles. And then we're going to multiply both sides by the molar mass. That gets us grams. So we have n mm over Na equals n naught mm over Na e to the minus kt. And so that becomes mass equals m naught e to the minus kt. So here's an example of using that mass equation. 1.0 gram of tritium is stored for 5.0 years. What mass remains? So originally a gram of tritium was placed somewhere. 5 years later, we're calculating what mass remains. We have the rate constant for the process that this tritium undergoes. to be this value 0.0564 1/year. Tritium is an isotope of hydrogen, and it is hydrogen 3, that is, it has 2 neutrons and a proton in its nucleus. It is the form of hydrogen that is unstable. Hydrogen comes as H1, stable, H2, stable, H3, unstable. H2 is called deuterium. Okay, so we use the equation m equals m naught e to the minus kt. Putting in our values, we have m equals 1.0, e to the minus 0.05641/year times 5 years, 5.0 years. So we get that the mass is 0.75 grams. That's the amount remaining, or we could say 75% is still remaining. Okay, half-life. Radioactive decays are normally discussed in terms of half-life of the nuclide of the isotope rather than in terms of the rate constant. So from half-life we can get rate constant, from rate constant we can get half-life. And we often look up information having to do with the rate of decay of a particular isotope and find we're given half-life, and from that we can find the rate constant. So a reminder, half-life, T sub 1/2, is the time needed for the mass or the number of nuclei or the rate to drop to 1/2 its original amount. And being first order, the half-life is ln of 2 over k. ln of 2 is to 3 figures 0.693. As k increases, so as the rate constant goes up, that the half-life decreases. So big, fast reacting isotope means it has a small half-life. The shorter the half-life, the more quickly it reacts. Okay, so our question here is, what is the half-life of tritium? We have the rate constant. So we take our equation, ln of 2 over k, and we put in the rate constant, and we find that tritium has a half-life of 12.3 years. That is to say that it will take 12.3 years for an amount to decay to half that amount, or its mass to decay to half of the original, or its rate, its amount of particles given off per time to decrease to half its amount would take 12.3 years. And we have the graph there on the left, and we have some different nuclides and what their half-lives are. A free neutron, so just one out there in interstellar space, would have a half-life of 12 minutes before it undergoes the decay process. So if we have a certain amount of neutrons, 12 minutes later, half of them have decayed. Potassium-40, we see its value, 1.26 times 10 to the 9th, that should have said years. Carbon-14, the one used in carbon dating, its half-life is the 5730 years. All right, we'll talk briefly about carbon dating, radiocarbon dating, C14 dating. Dating of archaeological artifacts from wood, cotton, flax, etc. is done using C14. Some necessary characteristics of carbon-14 are that it's naturally occurring and is present in all living plants. It comes from photosynthesis. In a living plant, the ratio of carbon-12 to carbon-14 is about 10 to the 12th. Much more, of course, is carbon-12. The approximate constant supply of C14 in the atmosphere comes from N14. So N14 produces at a pretty constant rate C14. So we have about a constant amount of C14 in the atmosphere, and then plants take it in through photosynthesis. And it's radioactive. Its half-life is this 5730 years. And there's the process that carbon-14 undergoes to produce the beta particle. Carbon dating is good for dating relatively young things. So they have to be younger than about 65,000 years to have it be mostly accurate. The carbon-14 produced in the atmosphere enters living plants via photosynthesis, and it exits via decay. Alrighty, so some pictures showing that. So we have a living plant. So it takes in carbon, both C12 and C14, through photosynthesis, which is taking CO2 and water from the atmosphere and the plant and so forth, and it produces oxygen and glucose. So that's a way of getting carbon-14 in and carbon-12 in. Well, carbon-14 decays by the process shown there. So there's in a living plant, there's a steady amount of carbon-14 because carbon-14 enters, carbon-14 exits. But when the plant dies and then it's taken and made into maybe a clothing item or maybe some kind of a wood artifact, then the carbon-14 is not entering anymore, it's only exiting. And so the amount of carbon-14 decreases. And the ratio of the carbon-14 to carbon-12, or the other way around, can be determined by mass spectroscopy or by measuring the amount of beta radiation emitted. So here we have a problem. A 1.00 gram sample of carbon from wood from an archaeological site gave 7,900 C14 disintegrations in a 20-hour period. In the same period, 1.00 grams of carbon from a modern source underwent 18,400 disintegrations. Calculate the age of the sample. Okay, so if we look at the modern source of this wood, we have 18,400 disintegrations per that time period. And that's because the modern source has a lot more carbon-14. The old source, our archaeological piece, the one that we're interested in from this archaeological site, its amount of disintegrations, 7,900 in that time period, are much, much less because through the years it has lost a lot of carbon-14. So from this, we can calculate how long ago that piece of wood was living, and that gives a sense of how old this archaeological site is. So we're going to, because we have rate information, we're going to use that rate is equal to rate naught e to the minus kt. From the half-life of the carbon-14, the value 5730 years, we can find the rate constant, and we get that value 0.0001 inverse years. So we take our rate equals rate naught e to the minus kt, and we solve for time because we're after time. So we have time equals 1 over k, ln of rate naught over rate. We put in our value of k, we put in our two rates. Now, of course, you have to make sense of which of those two numbers, the 18,400 and the 7,900, which is the original rate, which is the current rate. Or, as we talked about before, the original sample would have the 18,400 disintegrations when it was just like the tree was just cut. Now it's down to 7,900. So the rate is 7,900, the R, whereas the R naught is that value 18,400. So we would calculate a time that the wood was once from a living tree to be 6,990 years ago. Next, we're doing another dating problem, but this time it is rock dating, and we are using uranium-238. Many rocks contain uranium, and if so, then the ratio of the lead to the uranium can be determined. So as we studied earlier in this chapter, uranium-238 decays by a series of steps to finally stable lead-206. And when we are using that process, that decay process, we assume that all the lead currently in the rock came from uranium. We have the half-life for this process to be 4.5 times 10 to the 9th years. So here's our problem. We have a rock that contains uranium-238 and it contains lead-206. So we can do the dating using that process, and it is found that the U-238 to lead-206, so the amount, the like N amounts, is 1-to-1. How old is the rock? What we have to do to solve this problem is just set an amount of uranium that is currently there to some value. Let's say we say the amount of uranium is 100. Well, since the amount of uranium to the amount of lead is 1-to-1, then that must mean that the amount of lead is 100. The N of lead is 100. So all of the lead has come from uranium, so that must mean that the original amount of uranium that was there is 100 plus 100, or 200. And we're after the age of the rock, and so we take our equation n equals n naught e to the minus kt, and we solve for time. We get time is 1 over k ln of n naught over n. So we find the half-life given, we find the rate constant given our half-life. So k is equal to 0.693 divided by 4.5 times 10 to the 9th years. And we get that to be 1.54 times 10 to the minus 10, 1 over year. So we have then t equals 1 over 1.54 times 10 to the minus 9, 1 over years, times ln of n naught, 200 over 100. So we find that t comes out to be 4.5 times 10 to the 9th years. Or we would say 1 half-life has passed since the rock was formed. Alrighty, so in this problem, we were given the ratio of the number of nuclei present, the value 1-to-1. So we would say that like the number of nuclei of lead to number of nuclei of uranium is 1-to-1. In this next problem, we are told that a rock contains 0.523 grams of lead-206 for every 1.000 gram of uranium-238. We're given the information where we can find, okay, like a mass ratio of those two, but the amount of lead we have now in comparison to the amount of uranium it came from in terms of N, well, we have to realize that, of course, the molar mass of uranium is different from the molar mass of lead. And so we have to convert from mass of lead to mass of uranium, taking into account the molar mass of the lead as well as the molar mass of the uranium. And that is to say, 1 gram of uranium doesn't produce 1 gram of lead. 1 mole of uranium decays to 1 mole of lead, yes. But for the mass comparison, we do have to convert using molar mass. We're told to assume molar masses are equal to the mass number for that isotope. So the amount of uranium that decayed to produce the 0.523 grams of lead is given by 0.523 grams of lead times the ratio 1 mole of lead equals 206 grams. Now we've got moles of lead, so we can do the mole ratio between lead and uranium 1 to 1. And then we convert to grams of uranium. So we have the 238 grams of uranium per mole of uranium. That means that we have 0.604 grams of uranium that must have decayed to produce that amount of lead. So the original amount of uranium is the amount that decayed plus the amount that's there currently of the uranium. And we have 0.604 grams plus 1.000 grams, or 1.604 grams of the uranium that must have originally been present to then have the 0.523 grams of lead and the 1 gram of uranium there currently. Okay, so M naught is 1.604 grams, M is 1.000 grams, because of course in our equation, our mass as a function of time equation, we are looking at the radioactive decay of the parent, the uranium. Alrighty, so we take that equation, the M equals M naught e to the minus KT. We solve for time, which is 1 over K ln of M naught over M. Putting in our numbers, 1 over 1.54 times 10 to the minus 10, 1 over years, times ln of 1.604 over 1, and we calculate that the age of the rock is 3.07 times 10 to the 9th years. Alrighty, so these calculations we've done, the rock dating, the carbon dating, those are in the realm of kinetics, of disintegration, activity, rates of reaction. In our next section, we're getting into the nuclear energy, the thermodynamics part. Enormous amounts of energy are usually released in certain types of nuclear reactions. Fission type reactions, fusion type reactions. The energy released is calculated by comparing the masses of the reactants and the products and using Einstein's equation E equals mc squared, or we could say delta E, the energy produced, is equal to delta M, the mass change, times c squared, where c is the speed of light. It is 2.9979 times 10 to the 8th meters per second. In the combustion of methane, CH4, delta H is negative 890 kilojoules per mole. This corresponds to a delta M of only 10 to the minus 8 grams per mole of methane combusted, which is very, very small. But the amount of energy released in a typical fission or fusion reaction is so enormous that delta M isn't so small to be measured. There's more of a sizable mass change given the much larger energy change. The enormous energy release, the delta E, comes from the nucleus's desire to ultimately form iron. So it turns out that big isotopes like uranium and plutonium are trying to become smaller to ultimately form iron, and small nuclei like hydrogen, helium, they're trying to become bigger to ultimately form iron. So small atoms go toward iron through fusion. Big atoms go toward iron through fission. Iron is very stable. The stability arises from binding energy, BE energy considerations. The binding energy of a nucleus is the energy needed to break the nucleus into its neutrons and protons. So the binding energy of a nucleus is the energy that is needed to break it apart into all of its components. The bigger it is, the more thermodynamically stable the nucleus is. So what we're going to do is calculate the binding energy for helium-4. So that is what amount of energy would it take to break helium into its 2 protons and its 2 neutrons. We're going to convert from units of energy ultimately to get the energy in units of MeV, that's mega electron volts per nucleon. Okay, so for now, we're going to be calculating the mass change in that nuclear process and then the energy change. So we have to be given the mass of the parts involved. The mass of the helium-4 is given to us as 4.00260 U, where U is the atomic mass unit. That is the unit with the conversion to grams I give below in the problem. 1 gram is equal to 6.022 times 10 to the 23rd U. So U, it's called atomic mass unit, that is just a very, very tiny mass unit. And so it takes many of them to equal a gram. So what we're told is the mass of the helium atom is equal to 4.00260 U. Now, that's the mass of the helium atom. That includes the mass of the 2 electrons. We're also told the mass of the hydrogen atom to be 1.00782 U's. And that would be the mass of the hydrogen nucleus, which is composed of only the proton, plus the electron. We're also given the mass of the neutron, so just a single neutron alone, it has the mass value 1.00866 U's. Over to the right of those masses, we're told that in this problem here, the mass of the helium is the atomic mass of helium, electrons are included, and the mass of the hydrogen is the atomic mass of hydrogen, electrons are included. Now, in our process, in our nuclear decay process, we need to use nuclear masses, and they are atomic masses minus the mass of all the electrons. So we have nuclear mass equals atomic mass minus the number of electrons times the mass per electron, where the mass per electron is 0.00054858 U's. the reason I'm not giving you the nuclear masses in this problem is because many problems in the textbook, perhaps on the quiz, are given with atomic masses, and from those you have to calculate nuclear masses. So I wanted to show you how to make that calculation. Nuclear mass is the atomic mass minus the number of electrons in that atom times the mass of an electron. Okay, so once again, in our problem where we're calculating the binding energy for helium-4, we have the reaction being the helium-4 breaking into 2 protons plus 2 neutrons. So we first calculate the change in mass. So we take 2 times the mass of a proton plus 2 times the mass of a neutron and subtract the mass of the helium-4. Now we are given atomic masses, so we have 2 times the mass of the hydrogen minus 1 electron, minus Me, plus 2 times the mass of the neutron, and then minus the atomic mass of the helium minus 2 Me because it contains 2 electrons. And that's in the unit, this atomic mass unit. So putting in the values for Me and doing all the multiplying, subtracting, and so forth, we would find that the change in mass is 0.03036 U's. And then we use that conversion to go from U's to grams. So we're dividing our delta M in U by 6.022 times 10 to the 23rd. And we get the mass in grams to be 5.0415 times 10 to the minus 26 grams. Well, turns out we have to convert to kilograms, and that's because we want to calculate the energy in joules, and joule, 1 joule is composed of 1 kilogram meter squared per second squared. So the joule has kilograms within it, so we have to convert to kilograms. So we take our grams and we divide by 1,000, and we get 5.0415 times 10 to the minus 29 kilograms. Okay, now that we have the mass change in kilograms, we are ready to determine the energy change. So we use the Einstein equation. Delta E is delta mc squared. We put in our M of 5.0415 times 10 to the minus 29 kilograms. And we multiply by C, 2.9979 times 10 to the 8th meters per second. We multiply by C squared, so we're squaring that quantity. And if you look at units, we will have kilograms meters squared per second squared, which is the unit of joule. So we replace that with joules. So our number comes out to be 4.531 times 10 to the minus 12. That's joules, but in our problem we were told to convert it into units of mega electron volt. An electron volt is a very small energy amount, and mega electron volt, 1 mega electron volt is 1.602 times 10 to the minus 13 joules. So we're making that conversion. So we divide by the 1.602 times 10 to the minus 13, and we get that the delta E is 28.28 mega electron volts. That would be the delta E per helium that breaks down. But we were told in the problem that we should report it per nucleon. So when helium-4 breaks down, it breaks down to 4 nucleons. So we take that 28.28 MeV and we divide by 4 nucleons, and we get that the delta E is 7.071 MeVs per nucleon. Now, I know this problem had a whole lot of parts to it, so definitely go over that problem. Make sure that the different parts that are in it make sense to you. Otherwise, please email me about that. And make sure that you can ultimately get the problem and understand what it's about, so that you're ready to calculate the binding energy in typically these MeVs per nucleon unit for some other nucleus. So these binding energies are calculated for many nuclei, and values there are given, like if it's deuterium, so hydrogen 2, its binding energy to break down into a neutron and a proton is 1.2 MeVs per nucleon. We calculated it for the helium-4, 7.1. Iron 56 is 8.8. Uranium is 7.5. So if we look at a graph of binding energy in the unit MeV per nucleon versus mass number, so we have, there's deuterium, the hydrogen 2 on the bottom left, with its value of that 1.2, and we're seeing helium-4 higher. Uranium, its value of 7.5 is shown there. So what we have, if we calculated it for lots of different nuclei, we find that it goes up for the small, and then for the very big ones, it also climbs up as we go toward iron, because iron 56 is the most stable of all the nuclei, in that it takes the most energy to break it. We would say that that means that it is the most stable isotope. And so what that reveals to us is energy that nuclei, small ones, are trying to become more stable. They're trying to go toward iron by combining with each other to produce bigger and bigger and bigger nuclei up to iron. And the big nuclei, they're trying to become more stable by breaking down, ultimately, again, to end up at the iron. So energy is given off as small nuclei transform into bigger ones toward iron, and that process is fusion. So we have a small nuclei forming bigger nuclei, giving off lots of energy. That's what's occurring on the sun. It's being tested here on Earth with magnetic fusion, laser fusion, and so on as a possible future energy source. I show a reaction there of two H2s undergoing the fusion to produce helium-3. Energy is also given off as big nuclei transform into smaller ones, and this process is fission, and this is what's occurring at a nuclear power plant, for example. That's uranium or maybe plutonium breaking down to smaller nuclei, giving off lots of energy, and then we tap into that energy, the nuclear energy. It's also the process that occurs in nuclear bombs. I show an example of uranium-235 being hit by a neutron that sets it off to be unstable, and it, in this reaction, is producing the barium-142 and krypton-92, several neutrons plus lots of energy. Okay, so this this graph here, again, binding energy versus mass number, is just showing fission is occurring for the small isotopes, and fusion is occurring for the small isotopes, fission is occurring for the big ones in an effort to get toward iron. This describes why there's so much iron on Earth. Fusion is what's occurring in the sun. Fission is shown here, U-238 being bombarded by a neutron to produce an unstable nucleus, which breaks apart, producing two small nuclei and lots of energy. We can calculate the energy given off by these processes by subtracting the total mass of the products from the mass of the original nucleus and converting it into energy using the Einstein equation, delta E equals delta mc squared. So our problem here is to calculate the Q in, we're told, units of kilojoules per gram and kilowatt hours per gram when 1.0 grams of U-235 undergoes fission according to this reaction here. So we see the uranium plus a neutron forming barium and krypton and two neutrons plus lots of energy. In this problem, we're given atomic masses, again in that energy unit, the atomic mass unit, U. So we're given the atomic mass of U-235 to be 235.04 U's, of barium 142 to be 141.92 U's, krypton 92 is 91.92 U's, and we're also given the mass of a neutron. So we first off calculate the mass change. So that's going to be the mass of barium, so the nuclear mass of barium plus the nuclear mass of krypton plus 2 times the mass of the neutron minus the nuclear mass of uranium minus the mass of a neutron. Okay, since we're given atomic masses, what we have to do is take the atomic mass of uranium, subtract 56 times the mass of the electron, and then, no, I said that wrong. Okay, delta M, we're looking at products minus reactants. Okay, so we have the atomic mass of the barium minus 56 times the mass of electrons, because the barium has 56 electrons. Okay, so that takes care of the barium. And then we have the krypton. We take its atomic mass, 91.92, subtract 36 times the mass of the electron. So that's taking care of the krypton. That gets it into the nuclear mass. And then we have plus 2 times the mass of the neutron. Okay, so that's all of our products. Then we have minus the atomic mass of the uranium, 235.04, minus 92 mass of the electron, and then plus the nuclear mass of the neutron. So we put all of our numbers in. We had the mass of the electron from the upper example given to us. So what we end up with is that delta M is negative because we have a mass decrease. It is 0.191 U's. We convert that into grams and then kilograms. So using our conversion that we were given in the upper problem, we're dividing by 6.022 times 10 to the 23rd, and then we're dividing by 1,000 to get into kilograms. So we have the mass change to be negative 3.191 3.18 times 10 to the minus 28 kilograms. What this means is, being negative, the mass has gone down, energy ultimately is given off. Mass has been converted into energy. That's what Einstein equation tells us. Mass and energy are interchangeable. Okay, so now we're calculating delta E, which using the equation delta E is delta mc squared. So we take our mass, this 3.18 times 10 to the minus 28 kilograms, multiplied by the speed of light squared, and we get negative 2.86 times 10 to the minus 11 joules. That would be joules per reaction. We are told it should be expressed in kilojoules per gram. So this is the joules per reaction, or we could say the joules per nucleus. So what we have to do first is convert to number of moles. So we multiply by 6.022 times 10 to the 23rd nuclei per mole. Now notice nucleus is gone. We have joules per mole. Now we want it per gram. So now we use the molar mass of the uranium, which we assume to be, which we're given there in the problem, that 235.04 grams per mole. So now we have grams as our unit, and finally we make the conversion to kilojoules by dividing by 1,000. So we get that the delta E is negative 7.33 times 10 to the 7th kilojoules per gram. We can drop the negative sign. It's simply telling us that energy is given off. So delta E in this unit of kilowatt hours comes from here. So we take our conversion, our energy in kilojoules per gram, and we multiply by the conversion between the kilowatt hours and the kilograms, or kilojoules. So 1 kilowatt hour is 3,600 kilojoules. So that turns out with a delta E of 20,000 kilowatt hours per grams. And that is approximately the amount of energy that can serve 10 to 20 homes for a month. So kilowatt hours, the problem had us convert to that simply because when we pay our PG&E bill, we're probably paying it in units of those kilowatt hours. And again, 1 kilowatt hour is 3,600 kilojoules. So that's how we could calculate delta E in that fission reaction. So this diagram is showing you just a fission reaction again with uranium getting hit, getting hit by a neutron. That neutron sets off the nucleus to elongate. It makes it unstable. It eventually breaks down. And if we have what is termed a subcritical amount of nuclei or subcritical mass of the uranium, then if we have a process where one neutron causes a uranium to break down, undergo fission, giving off 2 neutrons, if we have only a little amount of the uranium present, then we could imagine a lot of those neutrons that are formed are just escaping. And if we don't have enough uranium, if we don't have enough neutrons that are kept within that mass to cause nearby uraniums to undergo fission, the fission will just stop. And that's what happens when we have a subcritical mass. Too many neutrons escape, and so they don't sustain the fission process. If we have a critical mass, then enough neutrons are staying within the mass because we have a big enough mass of the uranium that they're formed, they're absorbed, and so it's self-sustaining. If we have too big a mass, a supercritical mass, then all of those very few neutrons escape, most of them are contained, and we have a fission process that can be out of control. The critical mass of uranium-235 is about the size of a grapefruit. Natural uranium is about 1% U-235 and about 99% U-238. The big difference between those two isotopes of uranium is it's U-235 that undergoes fission. U-238 simply undergoes the alpha and beta decay process, not producing those tremendous amounts of energy. A nuclear energy reactor, that is controlled fission, the one where we have the critical mass and it's just self-sustaining, it's not dying off, it's not going out of control, that needs about 3% U-235. So when uranium is found in nature, it has to be enriched to be able to be used in a nuclear reactor. In a bomb, on the other hand, where the desire is to have it react very quickly and explosively, because a supercritical mass is required, it needs about 90% of the uranium to be U-235. So a lot of enrichment is occurring there. This diagram is showing a fission reactor, so one where we get nuclear energy from it. What I want to point out is the sample is shown as those yellow rods, and each one of them would be big enough to sustain the reaction, and the control rods are a material that can absorb the neutrons that the process gives off. And if too many neutrons are being absorbed, then the reaction starts getting too fast. So then the control rods are moved into the sample area more to slow it down, to keep it controlled. So the control rods can be pulled up and down to keep it just self-sustaining. Lots of heat energy is produced. That heat energy ultimately goes to water that causes steam to form, and that then can, by pressure changes of the high pressure steam, it can cause a turbine to be spinned, which is like a big blade of like a jet blade. It's a huge blade that is then hooked in up with a magnet, and we have a magnet that can be converted as it accelerates into electrical energy, and that's how we get electrical energy out of the process. So this is showing the uncontrolled fission. So a neutron hits a nucleus, producing fission to occur, which gives off neutrons. If those neutrons are pretty much all absorbed within the mass, then we get this reaction that's spiraling out of control, and that happens when we have a supercritical mass. So that would happen in a bomb. These last diagrams are showing the bombs that were dropped on Japan at the end of World War II. There was the Little Boy, which was a uranium-235 bomb, and it contained subcritical pieces of uranium that were then driven together by a chemical explosion that caused the subcritical masses to be forced together, and that then gave rise to a supercritical mass that underwent the fission. Here is the Fat Man, that's the plutonium bomb, and it also had the subcritical masses, the chemical explosive that caused those subcritical masses to be combined into a supercritical mass that then underwent the out of control fission. Alrighty, so that's it for this chapter. So go over this video again, read your handout notes carefully, go back and do all the examples, making sure that you're comfortable with them. Read the chapter in our textbook, do the assigned homework problems, and when you're ready and the quiz is open, take the quiz. Keep an eye on when it's closing so you make sure you get it done before it closes.